Okay, let's continue now with the discussion of Markov chains, which we started last time. So a Markov chain, and specifically a discrete time Markov chain, so the times are indexed by the positive integers here. It's a discrete time process with this property, so saying that the conditional distribution of the next step given the entire path depends only on the present state. And so the easiest way to describe this is through what are called the transition probabilities. In particular, we're going to assume time homogeneous transition probabilities, meaning that the conditional distribution of the next state given the present state doesn't depend on what time it is. So we see that here that if we're currently at time t and we're in state x at time t, then going to state x prime at time t plus 1, the conditional probability is equal to the conditional probability of going from x to x prime from the initial time point, and this is true for all t. So we can define this transition probability just by a two-place function, and we write this as p of x prime, meaning that's the probability of a transition in one step of going from state x to state x prime. So what we've shown previously is that it's convenient to arrange these transition probabilities in a matrix, particularly in the case where the state space is countable or finite, and we're gonna specialize to the finite case later on. But we call this the transition probability matrix. So you can think of the rows being indexed by the current state, the columns indexed by the next state, and the entry the ij entry would be the transition probability of going from state I to state j. And a stationary distribution for a probability distribution is called stationary for this Markov chain if if it's invariant under transitions by this matrix. So think about if I were to start in a random state according to a distribution pi, and then I make a transition to the next time through this transition probability, then the marginal distribution of the next state that I visit, is still distributed according to pi, and so it's stationary. It's not changing. Once I draw something according to that distribution, then the marginal distribution at all times after that will be the same, and it will be given by pi. So that's what it means by stationary. And a lot of what we talk about when we study Markov chains will be characterizations of the stationary distribution in one way or another, or situations in which there exists a stationary distribution, and how fast the Markov chain might converge to a stationary distribution. That's important in for example, in the technique in Markov chain Monte Carlo, where we actually set up a Markov chain which is converging to a particular distribution with the interest of sampling from that distribution. So that's one particular application of Markov chains. So in order to study this analytically, we define different characterizations of the states of the Markov chain. So we said one thing, we said that we have two states, and we said that one state was accessible from another. So x prime is accessible from x. So I write it this way. If there is a path that has positive probability, so we can go from x to x1 to x2 to x3 to x4, so on and so forth, to x prime, finite path such that each transition has a positive probability of happening. And so since each transition has a positive probability, the entire path has a positive probability. So there is a positive probability once I visit state x that I'll eventually visit state x prime. And we say the two states communicate if they're both accessible from one another. So if x prime is accessible from x, so I can get from x to x prime with some probability, positive probability, and then once I get to state x prime, I can get back to state x also with positive probability. And that's an important property to have for stationary distributions, as we'll see, because in order for a Markov chain to be in stationarity, if I can get from x to x prime, so there's some positive probability in stationarity of me being in state x, and then some positive probability of me being in state x prime, because I can get from x to x prime, then there better be a way of me getting back to x from x prime, because if there's not, then that can't be a stationary distribution, and we'll see how that comes in more formally later on. And we call the Markov chain irreducible. I realize this is a little bit hard to read here. We call the Markov chain irreducible if all of its states communicate. So the idea there is that if you think of the chain, the state space as a graph or as a set, and we're moving around all the different points in this set, if all of the states communicate, that means no matter where we're at, there is some path that could take us from anywhere to anywhere else in the state space. If all the states didn't communicate, then that would mean that once we reach a certain state, there's going to be some other states in the space that we could never reach. And so, in effect, the state space has been reduced down to a subspace, and we don't want that generally when we're studying stationary distributions, but we generally don't want that when we're designing Markov chains. Okay. So the first thing that we actually talked about this last time was that if two states communicate, then they have the same period. So remember, we define the period of a state to be the greatest common divisor of the number of states that I could come back, revisit a state, go from x to x in some number of steps. And so this is all review from last time, so I leave the details. I'm not going to go over the details, but this was something we discussed last time. So therefore, if all states communicate, so if the chain is irreducible, then all of the states have the same period, and so it makes sense at that point to talk about the period of the chain as opposed to just the period of its individual states, because all states have the same period in that case. And the proof was left as an exercise. Okay. But there's two immediate consequences of this which are important to be aware of. The first one, if the chain is irreducible and there exists a state which has a positive probability of staying where it's at in one step, okay, then the chain must be aperiodic. Okay. And the proof of this is immediate, and you should think about it. I think I may have even given this as an exercise last time. But what's the idea is that if you have a chain that is irreducible, meaning that all of its states communicate. So we know from the previous proposition that all of its states communicate, so that all states have the same period. And if we have one state that can possibly stay in the same place during one step, meaning that there is a chance of just staying where you're at in one step from one state, then that means that that state has period 1, and since it's an irreducible chain, all states have the same period, and therefore all states have period 1, and therefore the chain is aperiodic. The next corollary of this is that if x has a stationary distribution which assigns positive probability to state x, and if x and x prime communicate, then the stationary distribution must assign strictly positive probability to state x prime. And the way to see this, I mean, the argument's pretty simple, is that by assumption, we make the assumption, we've already assumed that x and x prime communicate, okay, and what that means by definition is that there exists a path. So there's a path x0, x1, and so on up to xn, where we start at x and we end at x prime, and such that this path has a strictly positive probability. So there exists a path that takes us from x to x prime. That's by the definition of x prime being accessible from x. Okay. And we've assumed that pi of x is positive. And so by the assumption, by the definition of stationarity, pi, this is just the definition of station. This is what it means to be a stationary distribution, right? This is exactly what we saw up here. This property holds for a stationary distribution, and then we can also apply p. We can iteratively apply p on both sides, and we see that this holds again and again and again. So it actually holds if we put an n up here. So it holds for the n step transition probabilities. So this is a path that is of length n plus 1 or n or something, but it doesn't matter exactly what it is. So this relationship holds because pi is stationary, and this is the sum over all states x star. So this sum is a sum of strictly non-negative quantities, so it's certainly at least as big as one of its terms, which is the term where x star equals x. Okay, but this transition here is just one. So this is the probability of making a transition from x to x prime in n plus 1 steps. We've already identified one such possible transition. So this is one possible path from x to x prime, but there could be many others. So this is another inequality, but both of these are strictly positive, and that's all we need. And so we're done. Okay. So now that was just review. Going into now specifically finite state Markov chains. When we talk about finite state chains, actually we can do a lot of things a bit more analytically because we're dealing in a finite state space, and we can leverage certain techniques from matrix theory, but here we don't even really need that. It's really a consequence of some basic analysis where the state space, and particularly the space of probability measures, so the space in which the stationary distribution lives, is a compact set, and so that's going to allow us to say some pretty specific things about the convergence behavior of the chain. So I'm going to assume a finite state chain. That just means that the state space is finite. There's finitely many states that we can visit. We're talking in discrete time, indexed by n here. And I just remind you of this notation where the probability operator indexed with a superscript nu, that means that's the distribution of the state at time. So there's a state at time n of the chain for each n. And this is under the assumption that the initial distribution is nu. Okay, so what we've done here is we first draw an initial state at time 0 according to the distribution nu, and then we take a step from the n step probability from whatever state we pick to x. And that's the probability. This is the marginal probability of the state at time n. And the main theorem that we're going to talk about here is that if we have an irreducible chain on a finite state space, then the chain has a unique stationary distribution. So all finite state irreducible chains have unique stationary distributions. Okay. If the chain is also aperiodic, then for any initial distribution we have this condition, which says that the limit under any initial distribution of the probability of being in the state at time n is the stationary probability. Okay. And this is a property that's called ergodicity. So chains that satisfy this are called ergodic. Okay. And so what that means is that the significance of ergodicity, in particular in this case, is that if it holds regardless of the initial state, and it's a limiting property that holds regardless of where you start. It's important to, at least before we discuss and try to prove this, what's the difference between these two statements? So saying that x has a unique stationary distribution denoted by pi is just saying that there's some vector or some distribution pi that is invariant under the action of the transition probability of the transition matrix. Okay. But that's a weaker statement than saying this limiting statement down here, which says that for any initial state, and any initial distribution, could be a deterministic initial distribution, that the limiting behavior goes towards some stationary distribution pi. And the way to see the difference is that if you could take a trivial Markov chain with two states, so say I have a state here, 0 and 1, and what I do is I deterministically jump from this state to this one, and then when I'm there I jump back, and so I just go back and forth between 0 and 1 deterministically. So at time 0 I'm at 0, at time 1 I'm at 1, at time 2 I'm at 0, at time 3 I'm at 1, and so on. Okay. So this chain will have a stationary distribution which will have probability 1/2 and 1/2 on each of the two states. But that is not the probability that you're in either of those states at any given time, because it's a deterministic chain. You know that during even times you're going to be at state 0, and during odd times you're going to be at state 1. And so this limiting statement here will not hold in that case because it's a periodic chain. It has period 2 because we see that every state is only visited in increments, in time increments of length 2. Okay, so the 1/2 there, it means something. What it means is that in the limit you'll spend half your time in state 0 and half your time in state 1. But it doesn't have this stronger condition as the actual distribution of the state that you're in at some large time in the future. That's where you need the extra aperiodicity assumption. Okay, so what we want to do is prove this theorem. And so the general strategy that we're going to have is we're going to work with the space of probability measures on X. So this is what I'm writing as P of X, space of probability measures on X. We'll see that that's a compact set. And what we'll also observe is that by taking transitions in this according to this chain, it has the effect of shrinking the set of possibilities within this space of measures. We'll see what we mean by that in a second. And then because of this shrinkage property, and we're applying it repeatedly, eventually this repeated application of P shrinks this state space to a single point. And that single point is going to be the unique state. That's going to be the stationary distribution. Okay. Okay, so first to observe the properties of this compactness property of the space of probability measures. So first, just note that the space of probability measures on X is a finite set. We assume it has size capital N. So this is in 1-to-1 correspondence with the n-1 dimensional simplex, which I write here as delta n. So delta n is just the set of all vectors, S1 up through Sn, non-negative, add up to 1. Those are probability distributions on the numbers on the states 1 up through n. Okay, so since the state space is finite, we might as well assume it's labeled 1 up through n. It makes no difference. Okay, and that means that the transition matrix, of course, is then just an n by n matrix. Okay. And the key observation here is just that this space is compact for every finite n. Okay, and to see this is just basic consequence of real analysis. This is a closed and bounded subset. This space here is a closed and bounded subset of Rn. Technically, you would have to prove that, but that's easy to prove. That's not even an exercise, but could do it as an exercise if you'd like. But as we know from the Heine-Borel theorem, closed and bounded subset of Rn is compact, and so we're done. And so a key technique or a key observation that we're going to make in doing this is that what we're going to do is we're going to iteratively, when we when we make steps in a Markov chain, what we do is we iteratively apply, make a jump according to the transition probabilities, which algebraically is an application of a stochastic matrix to an element. You can think of it as being to an element of this simplex. So we start in a particular random state according to some distribution, and the distribution is an element of this simplex. Then we apply the stochastic matrix, the transition probability, to that state. That takes us to the marginal distribution of the states at time 1. And then we're going to apply that operation again and again and again. And the key thing to realize is that as we apply this operation, we're staying inside the simplex, right? So a transition probability takes a probability distribution on n states to another probability distribution on n states through this matrix multiplication operation. And so that's what's called, formally, that's a semigroup property of the space of stochastic matrices, which just means that it contains an identity. So the identity is a stochastic matrix. All the rows add up to 1. And it's an associative operation. And it's an associative operation. Okay. So in this case, this semigroup, the stochastic matrices, acts on the simplex by right multiplication. Okay, so if you give me a distribution nu, you give me a transition probability, I can get you to the next state by picking a random state according to nu and then transitioning according to p. And we're going to keep doing this over and over and over again. Okay, so that's the action that we take. Okay. Now what we want to do is we want to show that as we move along in this process, that the whole point of this is to show that the chain is converging to a particular distribution, that the marginal distribution is converging to something. Okay. And the way that we're going to discuss that convergence in this case is in terms of the total variation distance. So we've talked before about total variation distance, and here we just define it again. So remember, the total variation distance is the total variation distance between two distributions is just the maximum of all subsets in the state space of the maximum difference between the two measures. So you find the subset of the state space, and it's the maximum difference between the two measures. Okay. So it's the worst case scenario. It's the set it's the set on which they're the most different. But we have a convenient way of calculating that, which we've seen in earlier on, where we can actually, in the finite setting, we can just sum up over all states, and we sum up the absolute differences, and we multiply by half. Okay, so that is the total variation distance. Okay. And the theorem that we're going to use here, or we're going to prove, is that if we have a transition probability, so the first thing we're actually going to do is we're going to prove this theorem 8.2 in a simpler case. Okay, we're going to prove it in a case where the transition probabilities are all strictly positive. So the one-state transition probabilities are positive for all states. So that's what we're going to prove right now, and then we're going to generalize from there. Okay. So let P be a transition probability for which all entries are strictly positive. Then there is some alpha for which this relationship holds. Okay, so let's look at this for a second. Okay. So what this is saying is, let's say we were to start in distribution nu, and so we have two distributions, nu and mu. Okay, and what we're considering is starting the chain, one chain in distribution nu and another chain in distribution mu, and they can be anything. And so the marginal distributions of the two chains at time 0 are mu and nu. But now what we're going to do is we take a step in both chains according to the transition probability P. And then the marginal distribution at time 1 of both chains is going to be nu P in the one and mu P in the other. And so now what we can do is we can compare the distance that we started at, the distance between mu and nu, to the distance at the next time, the distance between nu P and mu P, which is the distance at time 1. And what this says is that the distance at time 1 is strictly less than the distance at time 0 because this alpha is strictly less than 1. Okay. It's geometrically decreasing. And then when we apply this again, the difference at time 2 is going to be alpha squared times this. And at time n is alpha to the n times this. So you can see that this difference is converging to 0, okay, assuming we can establish this theorem. Okay. But the upshot of this is that this operation of taking a transition according to a transition probability with strictly positive entries is a strict contraction. Okay, so it's contracting the simplex at a geometric rate, and that's what's going to give us the convergence that we need. Okay, and here's the proof. So by assumption, all the entries are strictly positive, so that means there's some epsilon, some positive epsilon, that all entries are strictly bigger than. And so what we know is that the sum of all the rows are 1, because it's a probability distribution, it's a stochastic matrix. And we also know that each entry is strictly bigger than epsilon, so the sum, each row sum is also strictly bigger than n, the number of states, times epsilon. And so this quantity 1 minus n times epsilon is some value that's strictly bigger than 0, and it's also strictly less than 1. Okay. Strictly less than 1 because we know that n times epsilon is positive. Okay. And so what we're actually going to do is we're going to define alpha to be 1 minus n epsilon. That's going to be the alpha that plays the role up here. And we define a new matrix Q, which is going to be it's going to be a new transition matrix where we take P, we subtract off the epsilon. The epsilon is the lower bound on the values of all the entries. We subtract epsilon from all the entries. So I have this matrix J here. This is just a matrix of all ones. Okay, so this has the effect of making all the entries be Pij minus epsilon, and then we're going to renormalize by alpha to make sure everything adds up to 1. Okay, so Q is again a stochastic matrix. Okay. And so what we have here then is we show that Q is a stochastic matrix. And now what we need to show is that the relationship that we want to prove, this relationship holds. Okay. And the fact that Q is stochastic will come into play. Okay. So this is really just a bunch of math, a little bit of math, basic arithmetic, where we have the definition of the total variation distance. I've taken the half from here. I've taken the half, and I multiplied it to the other side. So I have 2 times this total variation distance. This, by definition, is the difference between the difference of the two measures, the absolute difference of the measures at all the states. That's just by definition. Okay. But the definition of these marginal distributions here are, well, what is this? This is the probability that we're in state J at time 1. And the way that we're going to be in state J at time 1 is to first pick an element at time 0 according to nu, and then transition into J according to the transition probability. And in here we're going to pick according to mu at time 0, and then transition according to the transition probability. Okay? And so that's just the definition. This is rearranging. Pij is equal to, we've defined Qij so that this relationship holds. So pulling alpha over here, adding epsilon. Pij is equal to alpha q ij plus epsilon. And then we can break this sum up. We add an inequality because of it's the triangle inequality. And we see that when we do that, this actually disappears because the sum over all states of nu and the sum over all states of mu, both of them are probability distributions, so they both add up to 1. And so 1 minus 1 is 0. And so this part goes away. We have an alpha outside here. And then we can apply the triangle inequality again. We're applying the triangle inequality again. And then we're rearranging the order of summation. And it's a finite sum, so we can do that. Actually, all of these things are non-negative, so we could do it. But it's a finite sum, so we can definitely do it. And that allows us to see, since this is stochastic, this just adds up to 1. And this is exactly twice the total variation distance of mu and nu. And so we're done. Okay. So the key consequence of this is that, what's the key consequence of this? Is that it's going to allow us to apply the contraction mapping theorem in proving a version of theorem 8.2. Okay. And so I've stated the contraction mapping theorem here from real analysis, which is just if we have a compact metric space, xd, I'm writing here, and we have some function which is a strict contraction, meaning it satisfies this relationship for some alpha strictly less than 1, then there's a unique fixed point for the function. And moreover, this limiting result holds when we iteratively compose the function with itself. It will converge for any state x. It's going to converge to that fixed point. So this is contraction mapping theorem. There's a proof in the notes actually, but I'm not going to prove it here. This is a theorem from real analysis. Okay, but to see that we can see that this immediately applies because in our case the state that we're interested in is the space that we're interested in is the simplex, which we've defined the total variation distance on. So it's a metric space. It's a compact metric space. We've already shown that by Heine-Burrell. So we have a compact metric space, and we've shown by the previous proposition that it's a strict contraction. So this holds for the operation. So this function f is going to be the operation of the transition matrix, the transition operator, to the current marginal distribution of the chain. And so that function, that operation, is going to have a unique fixed point. And that unique fixed point is the stationary distribution. And so just to summarize this here, I'll summarize this here, and then we'll finish for today for this lecture. This is a weaker version of the main theorem. So remember, the main theorem was saying that a unique stationary distribution exists for any irreducible Markov chain on a finite state space. Okay. Here we only prove the weaker version, which is that if we have a transition probability matrix, a Markov chain, for which this condition holds, for which all of the entries of the transition probability matrix are strictly positive, then P has a unique stationary distribution. And this proof is just a combination of everything we've proven, discussed so far in this lecture. So X is a finite state space, so it's isomorphic to a finite set, first n integers. Its space of probability measures is just isomorphic, one-to-one correspondence with the finite simplex, the n-1 dimensional simplex, which we know to be compact. We've already shown that the transition probability now, since it has strictly positive entries, is a strict contraction. So by the contraction mapping principle, contraction mapping theorem, it has a unique fixed point. And we also know that this limiting result holds that this limiting result holds here, also by this theorem. So note that since all of the entries are strictly positive, this is an aperiodic chain, and so this satisfies the stronger property of the theorem that we want to show. So I'm going to stop there for this lecture. Next time we're going to generalize this. We're going to use this theorem, so we're actually going to build off this theorem to prove the general case. It just requires a little bit more work, and I'm going to go over that next time.